Hello APC Mechanics students in Unit 2 Newton's Laws of Motion, Class 13 Circular Motion, Part 2. Then Section 1 Tangential Acceleration. The tangential acceleration given by AT is r multiplied by alpha, where alpha is the angular acceleration, is due to the variation of the speed, which is the magnitude of the velocity. So usually we have tangential acceleration whenever an object is moving along a circular motion and it's speeding or slowing down. The tangential acceleration has a direction tangent to the trajectory. Then let's consider an object speeding up along a circle. In each of the following figures we have a car, which is the object moving along a circular motion and it's speeding up. Now first of all, let's represent the velocity. It's moving clockwise, then the velocity at different points would be tangent and in the direction of motion. Now always in circular motion, we cannot turn off one type of acceleration, which is the centripetal. It would be always pointing toward the center. Now if this object is speeding up, then it would admit another type of acceleration given by the tangential. Tangential means it's tangent to the motion, so either it's right or left. Because it's speeding up, then it will be pointing in the direction of motion like that. Then this is it for all the four cases. And the total acceleration would be determined graphically using tail to head method or completing the parallelogram formed by AC and AT. So in this case, the total acceleration would be pointing southeast, southwest, west-north, and northeast. Now, what about if the object is slowing down? The velocity would be always independent of the motion, would be tangent to the trajectory and in the direction of motion, because remember that velocity is an indication of the direction of motion. Centripetal acceleration is always toward the center, whether it's slowing up or speeding up or slowing down. Now, because this object has a variation in magnitude of the velocity, then it will admit another type of acceleration given by AT. It will be either to the right or to the left. Because it's slowing down, then that would be to the left. And the total acceleration in this case can be determined from tail to head method or by completing the parallelogram. Example 1. A 16 00 kg car is traveling over a hill that has a radius of curvature 25 meters. The car is slowing down as it goes over the hill. It slows down at a constant rate of 25 meters per second to a speed of 10 meters per second over a distance of 50 meters, ending at the top of the hill. Calculate the net acceleration of the car at the top of the hill. Then let me draw here, represent what's happening in a drawing. So suppose this is a hill, and the radius of the hill is considered to be constant and is given by 25 meters. Initially the car started from point A at a speed of 25 meters per second, and it will end at the top of the hill with a speed of 10 meters per second. Then notice that if the car is moving from A to B, it is moving along a circular path. Its speed is changing, so it has tangential acceleration and it has centripetal acceleration. We need to calculate the net acceleration of the car at the top of the hill, which is at the point B. The net acceleration at the point B would be due to two components, the centripetal acceleration and the tangential acceleration. Now the net acceleration is due to the centripetal acceleration. AC is v squared over r, and the tangential acceleration given by AT is r alpha. AC is v squared over r, but which speed we're gonna use, 25 or 10? Since we are asked to determine the net acceleration at the point B, which is the top of the hill, we're gonna use the speed, which is 10. Then 10 squared divided by 25, then the centripetal acceleration is 4 meters per second square. That would be at the top of the hill. Now what about the tangential acceleration? Is given by r alpha. However, we don't know the value of alpha. Alpha is the angular acceleration and can be determined by referring to the type of motion, because they're telling us at a constant rate, which means uniform valid motion. We don't have time. So basically recall that one equation of motion that doesn't involve time is given by v square x is equal to vx0 square plus 2ax delta x. But here we're talking about circular motion, then v would be upgraded to omega, then omega square is equal to omega 0 square plus 2 alpha delta theta. Alpha can be calculated from the type of motion, uniform valid motion, slowing down at a constant rate. Omega square is omega square 0 plus 2 alpha delta. Isolating for alpha, we get that omega square minus omega square 0 divided by delta theta. However, we have the speed, we don't have the angular velocity, but we know that omega and v are related via v is r omega, which means that omega is v over r. Now, what about delta theta? We know that the length of the arc is related to the angular position by that. This can be represented as theta or delta theta. Then delta theta would be s divided by r. What does s represent? S would represent the distance that the car covered from going from A to B, which is basically a distance of 50 meters. Then plugging all the ingredients and the numbers, we would get that alpha is minus 0.21 radian per second square. Why negative? Because it's slowing down. Now this can be replaced in the tangential acceleration, and we would have a value given by minus 5.25. They're not asking for AC or AT, they're asking for the net acceleration, and it can be determined using the Pythagorean sum, and eventually we end up with an acceleration given by 6.6 meter per second square at the top of the hill. Now section 2, unbanked curve. Vehicles on a horizontal circular unbanked curve are in circular motion. So this is an unbanked curve. Curve means it is circular, and unbanked means horizontal. Later we will study what is meant by the banked curves. What keeps vehicles in circular motion and attached to the circle trajectory is the static friction between the tires and the road, and that should be equated by mv square over r. Although the car is in motion but there is no relative motion along the radial direction, then for this reason it is static friction and not kinetic friction. So basically we're saying what makes this car attached to the road is the static friction. However, the car is moving. Why we're talking about static friction and not kinetic friction? The thing is that we are interested in the motion which is along the radial. So whether it's slipping along toward the radius or away from the radius, we're assuming that the car will be attached to the road and there is no slipping either toward or away, and this is maintained by the static friction between the tires and the road. As the speed of the car v increases, then the term mv square over r increases, which means this requires more of the static friction to be equated by mv square over r. Then this is basically very similar to what we have discussed in the previous video. If the car is moving along a banked curve and its speed increasing, which means this term given by mv square over r increases, which means that there should be more of the static friction in order for this car not to lose contact or slip away from the road. Unbanked curves are engineered with a large radius, which means mv square over r decreases, and this would require a less magnitude from the static friction to be equated by mv square over r. So usually whenever we have unbanked curves, they are designed or engineered in a way such that the radius of curvature of these curves is very large, because when r increases, this makes this term to decrease, which means that this would require less static friction in order to maintain contact with the road. If you remember in the previous video, we have said that as r increases, this term increases, not decreases. The thing is that we were talking about a different complete problem. We were talking about the motion of an object attached to a disk, in which this object is moving relative to the disk with a constant omega. And we said that because omega, which is the angular velocity, is kept constant for all points along the disk, as we increase the radius, the linear speed increases, if you refer back to the previous argumentation. However, here the argumentation is pretty different. We're claiming that the speed will remain constant. We want to change the speed of the car. We're just increasing the value of r. In the previous case, we were changing v and r simultaneously. However, here we're keeping v to be constant and we're increasing the value of r, which makes mv square over r decreases. So basically, just as a recap, in unbanked curves, it is more beneficial to increase the radius of curvature, and that would require less static friction. Now, example 2, a curve in a stretch of highway has a radius of 512 meters. The road is unbanked. The coefficient of static friction between the tires and the road is 0.7. Now remember that we're not interested in the coefficient of static friction unless we're at the edge of motion. Edge of motion is related to maximum or minimum values. Then what is the maximum speed that a car can travel around the curve without skidding? Indeed, maximum speed means that we are at the verge of motion. If you increase the speed more, then the car will lose contact with the road and it will slip away from the center. So we're interested in determining the maximum speed. Speed appears from the centripetal acceleration given by AC is v square over r, and whenever we're talking about acceleration and forces, we are interested in Newton's second law. In order to do Newton's second law, we need to utilize the forces acting on the car. Then what would be the forces acting on the car if we're considering a front view? That would be the pull of gravity down balanced by the normal push up. Here we're considering, okay, they mentioned that it is unbanked, so it's horizontal, and the static friction would be toward the center. Remember, this is not the horizontal, this is the central direction, and this is the vertical. And now we're ready to apply Newton's second law. What are the different forces acting on the car? We have the pull of gravity, the normal push, friction equals to ma. Along the centripetal direction, gravity is 0, normal push is 0, we have the friction equals to mv square over r. So the friction is pointing toward the center, which is the positive direction. And we're searching for the value of v. Maximum speed means we are at the verge of motion, the verge of slipping. Then we have that friction is mu s Fn, but we still don't have the expression of Fn, and this can be determined by referring to the vertical. Fn is Fg, they are balance forces. Fn is mg. So basically Fn here can be replaced by mg, and this expression now can be replaced here. M and M would cancel, then the expression of V is given by radical mu srg. What does this expression represent? This is the maximum speed allowed for an object to travel along a banked curve without skidding or slipping. And it's given by 52.3 meters per second. Now we get to the more interesting part, which is a banked curve, section 3. Circular tracks are engineered to be banked, and now we're gonna explain why. In a banked curve problem, the horizontal is taken to be the x-axis while the vertical is the y-axis. Remember that when we were discussing the motion of a block along an incline and the block it's moving down or up the ramp, we used to take the x-axis to be the ramp and the y-axis to be the perpendicular to the ramp. But here the problem is completely different. The car is not moving up or down the ramp, it's moving along a banked curve, and in such type of exercises or applications we take the x-axis to be the horizontal and the y-axis to be the vertical. In this case, the normal push will have a component along the centripetal direction. Now what are the forces acting on the car? We have the pull of gravity down, we have the normal push perpendicular to the ramp, and we have the friction to be down the ramp. Now why down the ramp? Because we're assuming that the direction of slipping the car would be away of the road. So remember, if this is not banked like this, we were assuming that the direction of slipping is away from the center, which is like this, if this is the center. Now if you tilt this unbanked curve to be banked curve, which means that the direction of slipping would be up the ramp. For this reason friction is down, and If this is the angle theta, which is the angle of inclination of the ramp, they form the Z shape, then that would be also the angle theta. Now also, that would be the angle theta if you do the geometry of the figure. This component, in addition to friction, will help to equate the term mv square over r. So basically, why banked curves are engineered to be, or circular tracks are engineered to be banked. If the circular path is not banked, friction would be the only force responsible for keeping the car along the circular track, which is being equated by mv square over r. But now, if the circular track is banked, notice that the normal push in this case will have a component toward the center direction, which is the x direction. So that would help definitely the friction in order to maintain contact and not to lose slipping with the road. Note that for a motion along a ramp, the x-axis is taken to be along the ramp, and here we're taking the x-axis to be the horizontal. So let's consider the following application. Example 3. For a car to safely negotiate in a curve of radius 25 cm at a speed of 13 meters per second and in icy conditions, no friction, what banking angle would be required? So basically, we're assuming there is no friction. But as we've mentioned, for circular tracks, the main force which causes the car to be, in order not to lose contact or not to slip or not to skid with the road, is the friction. However, in case of the banked curves, the normal push exerted by the banked curve on the car would be enough in order for it to help the car maintain this circular motion, because we know that there will be a component of the normal push toward the center. So we're assuming no friction, and what banking angle would be required. And in order to do so, we need to utilize the forces acting on the car. So although this car is tilted, and usually we expect that the FPD would have the X shape like this, but remember that for this particular problem, the x-axis would be the horizontal and the y-axis would be the vertical. For this reason, I have represented the FPD to be like that. We have the pull of gravity down, we have the normal push is perpendicular to the ramp, which is like that, and it would make an angle theta with the vertical. And the friction, here we have no friction. Now we're ready to apply Newton's second law. That would be the pull of gravity plus the normal push is ma. Along the centripetal direction, the pull of gravity is 0, the normal push, so that would be F cosine theta. So for this reason, along the center, that would be F sine theta and V square over R. And we're interested in finding the angle theta and the normal push. Because it's an unknown, we need to get rid of the normal push. This is our first equation. Now remember that this is a vector equation. It gives the birth of two linear equations, one along the centripetal direction, which is the horizontal, and one along the vertical. Now along the vertical, we would have an F cosine theta, which is Fg. So Fn cosine theta would be mg, which is equation 2. And now we're gonna divide equation 1 over 2. So that would be Fn sine theta mv square over r divided by Fn cosine theta over mg. So basically we've divided this over that, this over that. And notice now Fn with Fn, they would cancel, and sine over cosine would give us tangent theta, which is v square over rg. Then this expression would give us the value of the angle theta that is required in order for the car not to lose or to skid along an icy road, an icy banked road. V is 13, we have R, we have G, then theta would be the inverse function tangent, and the angle would be given by 34.57 degrees. So here what do we mean? If we have on an icy road due to the weather, and the road is circular, so we need to engineer the road in such a way when a car is traveling along the road, in order not to skid away from the center. So this circular road should be banked at least by an angle given by 34.57 degrees. That would help the car to maintain this circular motion, which is given by a value mv square over r. Now exercise 1, a car is traveling clockwise around a circular track of radius 1440 meters. When the car is at the northernmost point on the circle as shown above, it has a speed of 36 meters per second and it's slowing down at a rate of 1.2 meters per second square. What is the magnitude of the acceleration of the car? We know that along circular motion, the acceleration, the total acceleration, is due to the centripetal plus the tangential. They gave us the magnitude of the tangential because the tangential, it's about slowing or speeding up, and a tangential is given by 1.2 meters per second square. Now the centripetal acceleration can be determined from the formula v squared divided by r. At the northernmost point, the speed of the car is given by 36 to the power of 2. The radius is fixed to be 1440, so we have the value of AC, and it's given by 0.9 meters per second square. The magnitude of the acceleration can be determined using the Pythagorean sum given by AC square plus AT square, which is the radical of 0.9 square plus 1.2 square, and that would give us a value given by 1.5, which is D. Exercise 2, a car is traveling clockwise around a circular track of radius 1440. When the car is at the northernmost point on the circle as shown above, it has a speed of 36 meters per second and it's slowing down. What is the direction of the acceleration of the car? They didn't mention whether we're talking about the centripetal, the tangential, so for sure it's the total acceleration. Partly we have centripetal acceleration toward the center. Now the tangential acceleration would be either right or left. This depends whether we're speeding or slowing down. We're slowing down, then it's pointing left. And the total acceleration would have a direction like that, and in this case it's given by west south or south of west, which is D. On a level horizontal table, a toy race car of mass m moves with a constant speed v around a flat circular racetrack of radius r. The car is now going around a banked curve as shown in the figure above. The banked curve is higher toward the outside of the circular turn. The car now travels at a higher speed without sliding because the banked curve, we know that the key concept behind the banked curve because it allows a component of the normal force to point toward the center of the track. Exercise 4, on a level horizontal table, a toy race car of mass m moves with a constant speed v around a flat circular racetrack of radius r. Which of the following best represents the minimum coefficient of static friction required for the race car to continue to follow the circular path shown? So we need the minimum coefficient of static friction. By minimum, it means we are at the verge of motion, and they mention the coefficient of static, so we can directly use that friction is mu s Fn. But now, before we apply Newton's second law, let's utilize the FBD of the problem if we're considering a front view. That's the center, and that's the car. What are the forces acting along the car? We have the pull of gravity down, we have the normal push to be up, and we have the friction to be toward the center. Now F net is ma, which means the pull of gravity plus the normal push plus friction is ma. And now we're gonna project along the centripetal direction. The pull of gravity would be 0, normal push would be 0. The centripetal direction is the positive, so that would be Ff is m a centripetal. We know that a centripetal is v square over r. Then that would be mu s Fn is mv square over r. The normal push is equated by the pull of gravity, which is basically Fn is mg. Then mg equals mv square over r. M with m cancels, then mu s is given by v square over rg, and the correct expression in this case is given by D. And here let me point out something very crucial. The same problem we have solved earlier in the video, but we didn't say minimum coefficient of static friction, we said maximum speed. Whenever we're talking about the edge of motion in such type of problems, so let me do here an important note. So flat circular track, which is known as unbanked curve. We're talking about the edge of motion, the centripetal motion for sure, because the car is indeed moving along a circular track. So we can discuss two factors given by mu s and given by the speed. This coefficient would be the minimum. This speed would be the maximum. Why? Because we need friction in order to maintain this motion. So we're asking about the minimum value of friction. So this is reasonable. However, for speed, because we know that as the speed increases, the car might skid along the centripetal direction. For this reason, we say the maximum allowed speed. Both quantities mu s and v, they represent the edge of motion, but the interpretation is different. For mu s, because it is the coefficient of friction that helps to maintain this circular motion, we say that this is the minimum value required. For this reason, mu s would be the minimum value. However, for v, as the speed of the object increases, this requires a more magnitude of mv square over r. For this reason, we say this is the maximum allowed speed. But both, they belong to something called the edge of motion. Now, exercise 5, which is an exit ticket for today's video. A particle of mass m moves counterclockwise around a horizontal circle of radius r as shown above. The angular speed of the particle is given by omega t is bt, where b is positive and t is positive. So as time evolves, this is a linear function, which means that this will increase, which means the particle is speeding up. Which of the following best describes the acceleration vector of the particle for the moment shown in the diagram? We have a centripetal acceleration down. We have a tangential acceleration pointing toward the left because it's speeding up. How do we know that it's speeding up? Because omega is positive, and as time evolves, this will increase, which means it's going faster. So they're asking for the acceleration, which acceleration, centripetal or tangential. They're asking for the total acceleration, and it would be pointing something like that. Upon completing the parallelogram, then it has components directed toward the left and toward the bottom of the page at this particular point. If they're asking for another point, the directions would differ. Then that's it for me in this video, guys. See you soon and a new one.